Okay, last time we were looking at the link budget for a microwave link, how to plan the power. We took the vertical axis in that diagram as power, and then all the gains we had upward jump, losses we had downward jump, and using that kind of a diagram we said we can plan the budget of the power in different power. We call it the link power budget. And then we also define some ratios which will be useful to assess the quality of performance. What are the ratios? There was one called CNR, carrier noise ratio. Another one called C over N naught ratio. Another one called EB over N naught ratio. Bit energy to noise power density ratio. So those are the three ratios for performance analysis. And why do we calculate them? Using them we can calculate the bit error rate. Bit error rate is the final performance for the link, and bit error rate is related to these ratios using that probability graph. I think I gave you the case slide. Vertical axis was probability of error or bit error rate. Complex axis is one of the three ratios I gave you. It should be either CNR or C over N naught or EB over N naught. The shape is always the same. So using this graph we can find out the bit error rate when one of these three ratios are given to us. So that was the whole plan of calculation. So today we will redo it for satellite link. Last time we did it for normal microwave link between 2 points on Earth. Now we will change little bit in that calculation and do it for a satellite. Okay? You can write such a thing. Satellite link power budget. Satellite link power budget. One is uplink. Uplink. And downlink. Third one is complete link, up plus down. Link is known as round trip. It goes up and comes down. Going up and coming down is known as a round trip. First point to notice that when we plan the downlink, we have to use the power of the satellite, and satellites are power limiters because they collect the power from sunlight, and therefore the downlink has limited power compared to the uplink. That's one important point to remember. Therefore, you will use a lower frequency for the downlink. The reason being that when the frequency is low, the free space loss, so the absorption loss becomes less. So because the loss is reduced now, you can transmit at a lower power and get the same performance. We will make note of that because that's the exam question point. You can write. Satellites like the power limiter. Power limiters because their batteries are charged by solar power. Batteries are charged by solar power. Therefore, the downlink should use a lower microwave frequency. Lower microwave frequency than the uplink. When frequency is low, when frequency is low, the free space large, and atmospheric absorption loss are low. Therefore, satellite can transmit lower EIR. Satellite can transmit at lower EIRC. Lower EIRC. We have already written it. You can write that by the request. The question is, why should we use the lower frequency for the downlink? This is the answer. We wrote the answer. And typical frequencies we use will be C-band 4, C-band. There are two bands, C-band and KU band. C-band uplink is close to 6. 6 is the middle value. Downlink middle is 4, and there are channels around 4. KU band uplink is 40. Downlink between 11 and 12. is a 1411 band and 1412 band. 14 versus 11. The choice of these frequencies are because of the skynoid temperature. You see, but skynoid temperature versus the frequencies, we find that these frequencies are having low skynoid temperature. So the graph is going like this. Around 4-5 Kelvin. Around 5 Kelvin. Nice temperature. And the frequency here is around 1 gigahertz. This is the noise window. Region of frequencies where the noise remain low, we call noise window. The C-band is somewhere here. K-band is somewhere here. This is going up to about 14 here. Both C-band and Ku-band remain within the noise window. But in between you can't use because there are other microwave links on the ground. They have been already assigned. This value is 22 gigahertz. This is 60 gigahertz. At 22 gigahertz we have water vapor resonance. At 50 gigahertz we have oxygen molecule resonance. Those are special points, special values in the spectrum. This is noise due to the lower frequency noise is noise due to outer space. We call it extraterrestrial noise or cosmic noise. Extraterrestrial noise or cosmic noise. This noise comes from outer space. This noise come from our own atmosphere, so we call it atmospheric noise. This atmospheric noise, like water vapor, oxygen, they are all within our atmosphere. So this increase of noise temperature is due to our own atmosphere. This is due to extraterrestrial noise coming from distant stars. In between band is the noise window, and satellite communication frequency should be selected within that. Otherwise, you have to transmit higher power to overcome higher noise, but you don't have that much of power in the satellite. So this is the argument you have to put forward to the examiner in If they ask why do you select this band, like C band, KU band, what is the reason? Reason is this. Reason is we can't afford to have high noise frequencies, because high noise means we need high carrier power. High carrier power is not available due to the battery operation in the satellite. So that's how you have to argue. You can use this graph to support that argument. Support the argument saying that lower frequencies extraterrestrial noise will be picked up by the antenna. Higher frequencies, our own atmospheric noise will be picked up by the antenna. The best region to operate is the noise window. Within that, you select P and KU band, because these other areas are already occupied by other applicants. They are not free. Therefore, these bands are selected. That can be right there. If we do not select frequencies, in the noise window, we need higher carrier powers. We need higher carrier powers to overcome higher noise level. Therefore, C and KU band were chosen for satellite communication. Because they fall within the noise window. So one typical question is the choice of the frequency. Second typical question is why the downlink frequency needs to be lower than the uplink. So those are the things we just highlighted now. Right? And now we will look at the link power budget. The power budget is not different for the uplink or the downlink. So even if you study one link, that will be enough, because the diagram will be identical for the other link. Okay? Put a fan method. The link power budget diagram. Has the same details for the downlink. As for the uplink. Therefore, we will analyze one of the two links. We'll analyze one of the two links. Here we can take the vertical as power. This is from somewhere. capacity output from the power amplifier. Say we are taking an uplink. Assume we are taking an uplink. And although it is the maximum power it can radiate or it can put out, we may not operate the amplifier at the highest power. Because if we operate an amplifier at the peak power, it generates a lot of unwanted frequency. So we operate at a lower power than possible, and that difference is given as a loss. Although it is not a real loss. It is not a real loss, we reduce the drive to the amplifier and operate the power amplifier at a lower power. And it is known as the back off. So in the diagram we draw it as LPO. We call it back off loss. Back off loss. But you have to remember is back off loss is not a real loss. Not a real loss. It is just defined for the budget. For example, if you take a motor vehicle with say 1.5 liter capacity, it has a certain maximum capacity. High speed it can go, but you may not drive at high speed. You may drive at 60 kilometers per hour or 100 kilometers per hour, but it may be able to go to 1500 to 2000. So this value is the one specified by the manufacturer. The manufacturer says, my amplifier can produce 1 kilowatt, but you may not use 1 kilowatt. You may drive it at 500 watts. So then there is a 3 dB loss you introduce into the budget, but it is not the actual 3 dB power loss because you are not radiating that anyway. Right? Is that clear? Back off is something we introduce for the budgeting only, but it is not a real power loss. That's how we have to think. After that, like in the earlier microwave thing, we will have branching and feeder loss. Branching and feeder loss. Like last time. After that, transmit antenna again you have to add. Then there will be losses. Due to phase space loss. And there will be additional absorption losses. I call it additional losses like absorption. After that, we have gain of the receiving end. Gain of the receiving end, and this will be the power you receive. Call it PR. And this is also known as carrier power. I think these things were all there in the last time diagram, nothing new. If you remember the last time diagram, you will notice none of them have changed.
Yeah, how are you?
there may be a certain minimum threshold level that manufacturer has given. Threshold power level is the level expected, minimum level expected by the receiver, given by the receiver manufacturer. So what do we call this margin? This is the minimum for operation, but this is what you provide. That just we call phase margin. Last time we call it margin for phase and same thing, phase margin. That also has not changed from the last time diagram. This is also seen in this gap. This gap we noted last time, this was system here. Again, same definition as last time. P out minus 2 PE minus. That's the system gain. Power density multiplied by the bandwidth is 10. Therefore, this gap is bandwidth. Indeed. Noise power density plus bandwidth is KTB. KTB is a null. Therefore, this difference is CO is not right. CO is not right. This diagram is true for uplink as well as downlink. Any link you can analyze like this. You can write below P naught equals saturation power output. Saturation power output. From the high power amplifier. Then BO means back off. BO, back off. BACK dash OSS. In brackets you can write, this is not a real loss. but it is due to this operation of high power amplifier at lower drive. High power amplifier at the lower drive level. Then B and F, LBF means branching and feeder loss. Branching and feeder loss. LA means additional link losses. MF equals fade margin. GS equals system gain. C means equal minimum receiver threshold. Okay, so those are the important definitions in this. And something which has not come into this diagram is definition for capital M. It is defined now. It is known as figure of merit. Figure of merit is defined as gain divided by noise temperature for an antenna. In dB, is gain in dB minus noise temperature in dB Kelvin. Therefore, answer is this. Subtraction becomes subtraction. Answer will be dBk minus 1. dB Kelvin to the power minus. It is the merit figure for an antenna, receiving antenna. If the figure of merit is good, what does that mean? Antenna can pick up more signal because gain is high, noise temperature is low. So therefore that antenna can produce, high figure of merit antenna can produce good quality received signal. Low noise and high gain. A poor simple M means noise is higher than the gain. Therefore, it cannot produce high quality receiving signal. So, the receiving system having high figure of merit can receive better signal. Right? A receiving system, after you write that, you can write them for. A receiving system with high figure of merit produce better quality reception. High figure of merit produce better quality reception. Produce better quality reception. Capital T is the overall noise temperature, overall equivalent noise temperature of the receiving system referred referred to the front end, of the receiving system. Front end of the receiving system. Okay, we'll do an example to show how the diagram can be used. You can write example. So exercise. This is actually June 2005 question number 5 in the paper. So we'll directly take that and do. That will highlight how to use the figure. You can mention 2005 June question number 5. It says the uplink of a satellite. System has following parameters. Now we can write one under the other set of parameters. Earth station saturation output power. Earth station saturation output power. Earth station saturation output power from power amplifier. Equals 32 dBW. Next line, earth station back of losses equals 4.4 dB. Next one, earth station branching and feeder losses branching and feeder losses 2.83 dB. Next one, earth station antenna gain is 62 dB. Antenna gain 62 dB. Next line, atmospheric losses 0.6 dB. Free space loss 205.3 dB. Satellite receiver figure of merit. Equal minus 5.1 dBk to the power minus 1, Kelvin to the power minus 1, K for Kelvin. Bit rate 120 megabits per second. Modulation scheme 8 PSK. Question says, assuming that the receiver noise bandwidth is equal to the minimum noise bandwidth. Receiver noise bandwidth is equal to the minimum noise bandwidth comma, calculate the following. Number 1, EIRP of earth station. EIRP of earth station. Number 2, CON note at satellite. CON note at satellite. Third point, EBON note at satellite. EBON note at satellite. Fourth point, wideband CNR. Wideband CNR. Fifth point, illumination level. Illumination level at the satellite antenna. Illumination level at the satellite antenna. So those are the parameters given. Now, one important thing you must remember is, if the free space loss for a satellite is around 205, 206, and that means it's a KU band satellite. KU band has around 206. If it is C band, it will be somewhere around 200 or little less than 200. So if they don't mention the frequency, now this is the question where they didn't give the frequency. So people will get stuck somewhere when they calculate. If they don't remember what are the typical values you get for the band. So because this is 205.3, you can see they are expecting you to know that it is KU band. So that kind of little tricks are there in the exam paper. So frequency is not given. Instead, free space loss value is given by which you have to guess what is the band. If you know the band, you know the uplink or downlink value, right? So put a stand next. So C-band link. Free space loss will be around or below 200 dB. Will be around or below 200 dB. For KU band, it is around 205 dB. 205 dB. 206 could be sometimes 206, but around 205. So remember those values. Why is free space loss higher for the KU band? I gave you the equation earlier. Free space loss has 20 log F. The moment you have KU band frequency, higher frequency, it rises. So you should remember for C band it's around $200, for KU band higher. So remember that, you know which band the link will operate. So those are the subtle points. You might know all the theory, but if you didn't know that, you get stuck in this question and don't score anything, because you can't do, you might have remembered this diagram and everything, but you can't get the answer. Because some data it looks like some data is missing. But they expect you to know typical values, that is the idea. They expect you to know that uplink for C-band is 6 GHz. They won't give it. So those are the tricky things. So even if you know the theory, if the typical value is not known, you can't work out. So be aware about that. This question I gave you for that purpose. Okay, now you can fill that data on this diagram. Draw the diagram and fill the data. Mainly we took the question to practice this diagram, so now is the time to practice. Now enter the value. While you enter, you can keep calculating. 2 minus 4 is 28. Branching and feeder loss is given. 2.83. Power therefore you can find out. The antenna gain was given 62 dB. Directly doing these additions and subtracting. Remember, if you make one mistake, all answers will be wrong. Right? You don't get anything after that. So you have to do it very carefully for the examiner. And additional losses 0.6 dB. Minus 19.13 dB. The basic radius analysis. ER is not given here. Sigma is not given here. So those are details given. Capital M is given. Give capital M minus 5.1. This is G minus T. GR minus T is given. Additional data. We'll be using it later. then we have to calculate from the bottom now, the bandwidth. Now, question says it's QPSK. In QPSK, how do you find the bandwidth? Bit rate divided by 3, because Q means, it is 8 PSK, 8 PSK. 8 means 2 to the power 3. Therefore, bandwidth is bit rate divided by 3. This is the rest of the work. I am writing this way, you have to write this way. PSK means bandwidth will be bit rate divided by, because in 8 PSK we learned in the diploma that there are 5 bits. 5 bits will form one symbol. Symbol rate was 1/3 of the bit rate. This bit of diploma knowledge required. Bit rate is given 120 megabits per second. Divided by 3. 40 megahertz. Not given, therefore we don't know this value yet. We can start from the bottom. This is minus 228.6, which is 10 log K. Remember this special value. This is Boltzmann constant in dT. 10 log K. KTB is the noise power. K is already there. T and B you have to add. That will give you the noise power. Noise power density means? Noise power density means KC. KC. So that you can mark noise power density. You know means you add E, you will get noise power density. And noise power means you add further B. Then you get noise power N. K plus T is noise power density, plus B is noise power, because noise power is KTB. KTB. You start from K, then this is KT, this is KTB. Slowly you go up. And this one you can convert to logarithm. Can you find 10 log of this value? 10 log of 40 into 10 to the power 6 how much? 10 log of 40 into 10 to the power 6. Doesn't have to write it. Is it 76? 70. It is 76. You are adding 76 to this value. This value is not known, but D over T is. This is 6.77 minus 6 minus 12. It will be minus 109. Can you do it? Will you calculate? Minus 109. Could be minus 119.1. So we have filled everything now. Now we can start answering. You can go to the questions now. First one is EIRP of the earth station. Where do you find EIRP? It is PT. It is GT. PT plus GT is EIRP. So this is EIRP. This is EIRP of your earth station. Answer is directly that way. It is 6.77 dBW. Second part, CON not at the satellite. This is C not. This step is CON. We will write an equation for that now. C for CON now. What is C? C will be this value plus GR, right? C will be GR plus GR minus 119.1. This is the carrier power. This is the value we have already found. So that GR is not known yet. At GR, then this is the value. N naught. N naught here, the value is N naught equals C minus 228.6. C minus 228.6. Because minus 220 plus C will give us this energy. So CON naught you can directly find now. CON naught should be therefore this minus that. From the diagram, just subtract, you will get the answer. So you should say from the diagram CON naught equals C minus N naught. C minus N naught. And C and N naught are both there in the diagram. Just substitute the value. So C means GR minus 119.13. N naught means C minus 228.6. Just subtract, then you will find GR minus C value they have already given, that minus 5.1, therefore answer will be available. So find the answer, we will compare the answer. The answer should come to 104.37. Check whether it is 104.6. Yeah, find it here. The here means this minus that. This minus that. When you take this minus that, automatically this will be there in your this is already given to us by the examiner. Examiner has given figure of merit is this. So therefore write this one instead of CR minus. Some of you are still unable to find the gap. Gap means upper value minus lower value. Simple as that. You can't get the answer, maybe the reason is you forgot what the examiner gave you. The examiner has given you figure of merit. So GR minus T he has already given. So that may be the reason why you can't get an answer. In another question, he might not give something here. Certain place he will not give in the diagram. Otherwise, there is no question because everything will link up again. He will not give something. And in this case, he has not given, GR has not been given, T has not been given. But GR minus T has given. So likewise, certain places will be blank. And you have to manage that by writing subtractions, additions, you have to equate it. Then you will find what is missing. So don't think that he will always do this, right? He will give something else next time, but same diagram will be necessary. Right? Okay. Did you get the answer 104.37? Okay. 104.37. What is the unit? Last time I gave you the unit of CON, no? No? There is it. It is dB hertz. dB hertz. dB hertz. We proved it last time, so maybe you forgot that. dB hertz. But if you just write dB, there will be some marks we reduce, right? So CON naught is not a unitless ratio. Okay, go to next part. Next part is EBON naught. EBON naught, if you know CON naught, EBON naught is already known. There was a relationship between the two. And that we proved last time, you can borrow from there. CON naught to get EBON naught? N naught is there in both equations. Only C has to be replaced by EB. So what is the relation? C divided by what will be the EB? Written at which side? So that's the only thing you have to subtract. So take the CON naught, subtract the bit rate. Subtract the bit rate, then automatically it is EBON. it is CON naught minus SB B square. So answer should be 23.57. 23.57. So from the earlier answer you have to subtract 10 log of bit rate. Bit rate is 120 megabits per second. So take 10 log of 120 megabits per second. So subtract that value from the earlier answer. New answer is 6. Can you double check whether it is 23.57? It is one step, right? I don't know why you are delayed. It is early answer 104.37 previous answer. From that subtract 10 log of 120 megabits per second. Answer should be 23.57. One step. So if you do more than one step, that means something is wrong in your calculation. Double check it. Right? It's one step answer. And that answer carries only one mark also. Right? So not worth spending a lot of time, right? Okay. Fourth one is wideband CNR. Wideband CNR means basically the CNR. The carrier noise ratio you can find from this. This guy. This is CNR. You can find this gap, this value from this value, but you have to subtract. You have to subtract this point. This point means T minus 220.6 plus 76. This gap is 76. So therefore you already know this value. Subtract this minus that. Again you will get GR minus T somewhere in the middle. For that, substitute minus 5.1. Then you will have the answer. should be 28.34 dB. You can get the same answer by any relationship, right? Like EBON, once you know EBON not, OCON not, OCNR, finding the other two. If one of them are known, finding the other two is using the relationship. Either you can use this diagram or you can use any of the three relationships we derived last time and find. Because all three are performance parameters. If one is known, others are known anyway, according to that relationship. Okay? So therefore, if they ask one parameter and give more marks to that, second parameter they will give only 1 mark or 2 marks, because they know that it's just a conversion. It is nothing big for the second time. Even in this question, only 1 mark for the additional ratio. So what is the next part? This one is 28.34, right? 28.34 dB. And that answer will be just dB. Earlier answer also dB. Previous answer, the CON naught is dB hertz. Okay, last part. Illumination level at the satellite antenna. Illumination level means the power density. The last part, illumination level, that means the power density. Power density at the satellite antenna. You can use this chart. Is that you are illuminating the satellite antenna like this. Using your beam from here. That the illumination level is available here. We are to find what is that illumination level. In other words, power density. You are radiating EIRP over a certain distance d. EIRP divided by 4 pi d square will be the power density here. EIRP divided by 4 pi times distance square. But since there are additional losses here, you have to divide by the loss also, additional loss also. That's the power density. Take EIRP divide by 4 pi times the distance d squared of what it has traveled. It has traveled distance d, take d squared. Since there is an additional power of 0.6 dB that you must subtract. But you don't need to subtract free space loss now. Because free space loss part is already included. Problem is the distance they have not given, right? Distance they have not given. Instead they have given free space loss. From this you will have to find the distance. Then use that distance there and for the calculation. Free space plus is 92.5 plus 20 log x plus 20 log b. And this is given to us 205.3. Because it's 205 we know it's KU band. Uplink in the KU band is 14 gigahertz. So you must know that it should be 14 gigahertz and D is the only unknown. So can you find D from this formula? How many kilometers? How many kilometers it has traveled? take 20 log 14 because giga is directly substitutable in that equation. Just take 14 and substitute, not 14 into 10 to the power 9. You know the values you are expecting now. Like you are expecting something like 30,000-40,000 kilometers. Somewhere there. If you don't get that, that means you have made a mistake. You can't have a satellite at 4 kilometers. You got 4 kilometers. It's lovely. So likewise, judge it. It will be somewhere close to 36,000. Maybe 38, maybe 40, something like that. 31,000. Is it 31,175? Okay, correct. 31,175. So that is distance up to satellite. So then substitute that distance in that equation. Around 31,000.
So your
assumption you must write there because free space plus is around 205. It should be k you have to write that and then substitute 14, then get this answer and then substitute that answer here. EIRP should be taken from this point, but it is in dB, so you can't substitute dB there. So therefore, possible if you take this one as dB. In that case, dB can be written as dB watt per meter square. It will be EIRP value in dB directly minus this plus minus 10 log of 4,5 times this. The same equation you can write in decibels. It will be this minus this. So then I can substitute this directly with 86.77 here. This 0.7 directly there. And this simple D is the 31,000 answer. So that will give us the answer illumination level at how many watts per meter square. But it is in dB watts per meter square. Here dB means 10 log has been taken. It will be around minus 70 something, 70, 79, minus 79.2. Is that correct?
Jangan jangan apa nak? Jangan jangan. Oh, dua yang semua kan ni. Oh.
minus 79 point something. Unit should be dB W per meter square. dB watts per meter square. I'm not sure whether it is 79. One of you have got, so please double check. I thought it should be around 70, I feel. Typical values are around 70, 79 may be okay, but I'm not sure. Link by microwave like this. You find sometimes the earth itself will be obstructed, and in that case you think of a repeater. This is a microwave repeater. This is a microwave terminal. Terminal station A. Terminal station B. Terminal station B. But in the middle you might decide to install a repeater and make it like this. Okay. So that the link will go up like that. So that's the typical solution. You will put a repeater and get the signal across. So middle terminals like that we call repeaters. There are different designs for repeaters. There are actually three kinds of repeaters by design. There is one type called RF heterodyne repeater. RF heterodyne means RF signal comes in, gets converted directly into another RF signal and goes. It will be F1, it will be F2. Radio frequency to radio frequency conversion directly, no demodulation. You just convert the carrier frequency to another radio frequency and transmit. Second design is called IF heterodyne receiver, where you will convert this microwave signal to intermediate frequency, amplify, then convert to microwave again and transmit. The middle frequency is called IF. It's called IF heterodyne. Third method is called baseband heterodyne repeater. Baseband heterodyne repeater means the incoming microwave carrier you will down convert to IF, demodulate completely to baseband, then remodulate to IF, convert IF to RF and transmit. This is called baseband redesign. If you find the two places are very far and one repeater is not enough, you might put more repeaters. You might need to find more places where repeaters are good and put more repeater station. Maybe costly. Another alternative is, don't put the repeater on the ground, put the repeater in the sky. Things like this. Things like that, then you can have very far-reaching microwave. Those are the ones we call satellite TV. This is called uplink. It's called satellite is nothing other than same repeater at a height. But then they call it satellite communication because the technology for putting the satellite there is special technology. But analytically, theoretically, there is no difference. Uplink analysis and downlink analysis is same as microwave signal going to a repeater, then getting repeated to the next one. Maybe you did not realize it. It seems like two different technologies, but it's the same idea. Same idea. When you want to achieve long distances, you put the repeater in the sky. And that repeater could be again RF heterodyne, IF heterodyne, or baseband heterodyne. Okay? So you can do the idea. This idea, this analysis is true even for them. This is just to highlight you that satellite is nothing other than a repeater placed in the sky. Nothing other than a repeater placed in the sky. Sometimes rather than constructing 1,000 repeater stations, it may be worthwhile to send one satellite. Otherwise you have to clear a lot of earth, you have to go to mountains, get the power there, lot of problems. Yeah? So therefore maybe worthwhile one satellite to do that. And since you can't have repeaters in the sea, the only option there over the sea is the satellite. On the ground at least you can think of putting repeaters, but on sea it's difficult, right? But I think Tigers have done it, isn't it? So they have used that ship as a repeater. You saw the ship yesterday, right? And the news that ship they have captured from somebody. And they have been repeating their signals from there. So repeater in the sea. Special case. Can mention when two points have no direct line of sight, when 2 points have no direct line of sight, a terrestrial microwave repeater can be used as shown above to achieve the linking. Achieve the linking of A to B. two places, the two places are far away. The two places are very far away. The repeater can be elevated. The repeater can be elevated to the sky. Elevated to the sky. Then it is a satellite. Okay. The satellite is known as a bent pipe repeater. Bent pipe. Bent pipe repeater in the sky. Bent pipe repeater in the sky. You know why it is called bent pipe? Because it has to go up and bend down. Therefore it is called a bent pipe. Underline bent pipe repeater in the sky. So remember, satellite is a microwave repeater. Right? Elevated microwave repeater. But theory-wise, there are only three types of repeaters. So satellite will have to also belong to one of the three. You can write new paragraph. There are three repeater designs. Three microwave repeater designs. Three microwave repeater designs. Number one, RF heterodyne repeater. RF heterodyne repeater. The idea is you take the signal from one antenna and then send it to a low noise amplifier. Then convert it to a different frequency by mixing it with the local oscillator. F1 is coming, F2 is going out. Actually there is a band pass filter after this to get F2. You get F2. Then you power amplify it and transmit. This is RFC. High power amplifier. High power amplifier like CWT or magnetron. Then you couple it out. It is the basic theory of RF heterodyne. F1 RF frequency is coming, F2 RF frequency is going out. RF heterodyne, you can draw that. Most older satellites were RF heterodyne repeaters. This oscillator is known as shift oscillator. LNA means low noise amplifier. HPA means high power amplifier. LO means local. This is a mix. So conventional bent pipe satellites were like this. 6 GHz is coming, 4 GHz is going. 2 GHz is a shift oscillator. 6 minus 4. 6 minus 4 is 2. 2 GHz is in the middle. You can conventional satellite. Conventional satellites were microwave, RF superheterodyne repeater. Microwave 12 RF superheterodyne repeater. Example, F1 equals 6 GHz, F1 equals 6 GHz, F2 equals 4 GHz, F local oscillator equals 2 GHz, F LO equals 2 GHz. So 6 minus 2 gave us 4. Okay, then next one is IF heterodyne repeater. IF heterodyne repeater. IF heterodyne means you convert this to this output is IF. You have to then this output is intermediate frequency, not RF. And then you have IF amplifier. Basically called IF stage. But you don't demodulate IF stage. When you convert it to RF again, using a second local stage. Use another bandpass filter. Then use the high power amplifier. Then cancel it. Then you see the modification. Two stages came, two mixers came. In the middle there is the IF. It does filtering, sharp filtering as well as amplification. And this is very popular for radio, TV, etc. They are called transposer. Transposer. The common name for this kind of a repeater is transposer. Maybe you are watching television via a transposer, I don't know. If you are directly receiving from a place like Viduru, then you may be directly receiving from the transmitter. But if you are in Kandy or somewhere, you may be receiving it from a transposer because it is going through another one and coming. Normally IF transfer. They don't demodulate the video signal. They will go take it to the IF stage and then take it to RF again and retransmit. So usually a television operator or radio operator might have one big transmitter. All other things may be transposers. They are doing this. So you can write this is the block diagram of IF heterodyne repeater design. IF heterodyne repeater design. It is commonly known as the transposer, TRANSPOSER, transposer. Transpose means RF to IF to RF. RF to IF to RF. That is called transpose. Then third one, baseband superheterodyne. Baseband superheterodyne. Sorry, baseband heterodyne. Baseband heterodyne repeater. So you can guess what is happening. We demodulate and get the baseband. Then convert it to IF and then convert to RF and transmit. So somewhere here this part is the same. Convert to IF, convert to RF and transmit. Before that this stage will be now a base type stage. It is not a mixer, it is a module. Then baseband. Baseband signal here. And to get the signal to baseband, now you have the IF before this. Now we have this part is R. The response signal will come using a local oscillator here. Local oscillator 1. We call it to IF. Then using a demodulator we call it to baseband. Then convert to IF again. Then R. Now you can see RF to IF to baseband, again baseband to IF to R. Expansion of the early idea. This is very popular for microwave repeat. Microwave repeat. It's a popular design today. Even for satellite. Even for satellite, this is popular. Shift oscillator is now for local oscillator. Normally demodulator gets the carrier recovered. receive ISA, will transmit ISA. Now that you have got the baseband signal after demodulation, there are traffic which is called drop traffic. Drop traffic means certain traffic channels you can remove now and insert new traffic channels here. They are called insert traffic. If you have worked in the microwave thing, you would notice that there are certain connectors in the IS baseband stage. One connector says drop port, other one says insert port. Traffic can be dropped or inserted from there. Basically, this is like a highway. It's like a highway. The vehicles who want to drop to this town, will have to take the turn and come here. New vehicles enter in the next section of the highway will have to be inserted. And the highway is the backbone. So telecom backbone is just like a normal highway system, road highway system. Unfortunately, we don't have highways to compare. We don't have crossings. You would have seen in other countries the highway is going, and certain diversion road starts and goes down to divert to local cities. will take time to come here. But I am sure you have seen that. So drop traffic and insert traffic. In the satellite also it's possible now. Satellite is now like a switch, acting like a switch. So if this one is adopted by the new, this is the one adopted by new satellite, they are called OBP satellite, onboard processing satellite. Because there is a processing stage here, baseband stage. And conventional microwave links always use this. Microwave links always use. Right. Terrestrial microwave repeater. Terrestrial microwave repeater. Normally use this design. Normally use this design because they form microwave backbone. They form that they are part of a microwave backbone. Part of a microwave backbone. Backbone is like a highway. It's like a highway for normal traffic. In addition, new satellite known as OBP satellite. Onboard processing. Onboard means within the satellite. Onboard processing. Close the bracket. Has the above block diagram. Has the above block diagram. So new satellites and microwave repeaters normally have baseband repeater. Suppose it is the microwave terminal, not the repeater. How would you draw? If you ask to draw the terminal, look at the earlier diagram. Terminal A was there, terminal B was there, repeater was the middle one. Suppose you are drawing the terminal, microwave terminal, what is the modification? Shall we do it as exercise? Exercise you can see. Modify this to find the block diagram. Modify this to find the block diagram now. The microwave terminal station. Microwave terminal station. Within brackets you can write. Another station is also another station. I am talking about satellites now. Another station is also a terminal station. The station is also a terminal station. Did you mention that M means modulated, EM means demodulated? Please write if you did not write that. M means modulated, EM means demodulated. If you are not repeating, but you are just starting it as a terminal, you don't need this antenna. You don't need this antenna. You don't need this. You don't need to demodulate. So, you don't need to drop or insert because you are the one inserting traffic. Baseband stage will be there, then modulator, IF stage, RF stage, this is RF. But for the baseband stage, before the signal comes there, you have to do multiplexing because lot of channels come to the terminal. They have to completely multiplex this and then make the baseband and then modulate the baseband on the capacitor. So we call it baseband processing. Before processing the baseband signal, you should have baseband multiplex. Now the multiplexing theories you have learned in the diploma will come here. It's a big block. I'm just throwing one box. Multiplex. So the multiplexer will come various input channels from your localized theory. Input channel. So that is the terminal. The terminal will get, now for example, if you have a satellite station here, you will get traffic from various other customers. All their traffic you will have to multiplex first. Then prepare your baseband after multiplex. Then process it properly and then modulate. Processing means coding. Baseband processing means it's a coding. Normally, for example, we call it channel code. Because the signal will have to be changed in order to go through the RF channel. The channel coding techniques will have to be applied. You can do block diagram for a microwave term. So this is where traffic will start to go into the backbone. So it's like a place where people enter the highway, but highway starts from there. Terminal is a place where it starts or stops. All other places are repeated. Baseband multiplexer, then baseband processing stage, then modulator, then IF stage, then RF stage, and then on a new line you can say satellite station. The satellite station has 5 subsystems. Has 5 subsystems. Number 1, antenna positioning and tracking subsystem. Antenna positioning and tracking subsystem. 2, transmitter subsystem. 3, receiver subsystem. 4, baseband subsystem. 5, terrestrial communication interface. Terrestrial communication interface.
Interface.
Look at the station inside here. You can model the earth station like this. Subsystem. This terrestrial communication interface (TCI). It may be fiber or radio. This link to the local community. This is baseband section. Baseband subsystem. This is transmitter subsystem. Receiving subsystem. This is the duplexer. Diplex. This is antenna. This is antenna positioning subsystem. So the antenna will have to be tracking the satellite. Satellite may be moving. There needs to be tracking. So this is antenna positioning and tracking subsystem. It is a mechanical kind of subsystem that controls electronic system. So this is the basic block diagram of the circuit. 5 subsystems. Satellite also has 5 subsystems. We will discuss this after the break. Each one has subsystems. Bigger systems we have. We can test to mean subsystems. This means all are subsystems. You can give you a name. What is the first one you need? This one. Second subsystem. Third subsystem. 5 subsystems in a satellite earth station. Okay, we wrote them 1, 2, 3, 4, 5. Likewise, you can number. So this figure shows how they are connected, how the 5 subsystems are connected. And this link is to the local area, local community. To the local community. It may be connected by fiber or another microwave link. So traffic will be brought into the satellite earth station. Through this interface, they form the baseband, then go through this transmitter, goes this way. My earlier block diagram had only the transmitter, but actually an earth station has a receiver also. And some earth stations don't have a transmitter at all. If you don't have this subsystem, you call it RO earth. Receive only earth. Sometimes you have seen in the papers they advertise TV RO system. TV receive only. You can't transmit. So RO stations do not have the transmitter subsystem. TO earth stations do not have receiver subsystem. Then TRX earth stations can do both. But we have drawn a TRX. So just mention that. When both TX and RX, subsystems are present. It is called a TRX type. Earth station. TRX type earth station. Within brackets, earth terminal. Earth station, some people call it earth terminal. Close the bracket. In next sentence, in a RO means receive only, RO type terminal, RO type terminal, there is no transmit subsystem. There is no transmit subsystem. In a TO type, there is no receive subsystem. TX consists of IF modulator, up converter. We drew in the earlier block diagram. Up converter, signal combiner, HPA, high power amplifier, etc. The RX consists of, that means receiver consists of LNA, low noise amplifier, frequency down converter, IF demodulator, etc. IF demodulator, etc. Antenna, AP and T, antenna positioning and tracking. AP and T, antenna positioning and tracking. Subsystem consists of, subsystem make sure the antenna remain aligned ALIGNED, aligned with the satellite. Usually there is a tracking receiver. There is a tracking receiver, that's a separate receiver, tracking receiver, and a motorized antenna platform, antenna drive to do the tracking. Tracking means you keep aligned with this to do the tracking. Suppose you buy a home satellite television set. You get the antenna, then cables, and then electronic unit which is connected to your TV. So that is a terminal. What kind of a terminal is that? RO terminal. Then same block diagram, except that this EPI and baseband and the receiver, they are all combined into one box to make it small. And what do you call it in the market? This part comes separately. This one is called in the market. What do you have to buy? Called IRC, integrated receiver decoder. Because receiver and all this decoding part is now integrated into one. And this one is not fiber or radio, now it's just going to your TV. Again the TV interface will be there. So you can see, block diagram is a common thing, whether it's a big one or whether it is home TV receiver. So what we have learned is the general theory. And understanding the general theory is very important for you to understand these practical systems later, because there are several systems. If you are to study one by one and keeping them separate, it will be tough. So, study the basic block diagram like this. This is generalized. And then you can adapt it to any practical system you are installing for your design. That's the easy way. Otherwise you will think each system is separate. as I mentioned earlier, some people think satellite repeater is different from normal repeaters you see on the mountain. No, microwave signal wise it is not different. The different part is only this satellite construction, that is different. It's different from base station construction, but signal repeating is the same thing. Most of them today use baseband repeater. So once you identify a common thing like that, it becomes easier to divert your knowledge into different areas you want. So what I highlighted is that common part, which otherwise you will think it's two different theories. I have to read 2 books or 3 books in order to become aware of all these technologies. That's wrong approach. I'm sure you don't have time to do all that. We have work rather than reading a lot of books, isn't it? So therefore try to simplify like this. Then with minimum reading, you can top up with needed knowledge. That is it. Okay, have a short break. And we have to discuss the satellite now. Earth station is what we discussed. Next, after the break, we will discuss the satellite.
¿Cuál es el